You stand in the cold, sterile room of the GISP-2 laboratory in New Hampshire, watching as technicians carefully extract a cylinder of ancient ice from its protective casing. The ice is 11,847 years old, give or take a few decades, and it holds within its frozen matrix something that should disturb you far more than it probably does. A record of the day the world changed in less than a human lifetime. The scientists here don't speak in dramatic terms. They use words like abrupt climate transitions and stadial interstadial shifts, terminology so dry it could desiccate the very air around you. But what they're describing, when you strip away the academic language, is terrifying in its implications. Around 11,700 years ago, at the end of what geologists call the Younger Dryas period, global temperatures rose by approximately 10 degrees to 18 degrees in Greenland within a span of just 3 years. Not 3 centuries, not 3 generations, 3 years. Dr. Richard Alley, a paleoclimatologist who has spent decades studying these ice cores, once described examining the layers from this period as seeing a staircase in the climate record. You move your finger down the core sample, and the isotope ratios, those telltale signatures of ancient temperatures, shift so dramatically that for years scientists assumed there must be an error in the dating. There wasn't. The Earth's climate system, it turned out, could reorganize itself with a speed that made mockery of the gradual transitions we'd assumed governed our planet. But here's what keeps a small community of researchers awake at night, poring over data that most people will never see. This wasn't an isolated incident. As you dig deeper into the paleoclimate record, scanning back through not just thousands but tens of thousands of years, a pattern emerges. Every 12,000 years or so, sometimes a bit longer, sometimes shorter, something happens. The climate doesn't just shift, it convulses. The evidence isn't limited to Greenland ice. You find it in the sediment cores pulled from the bottom of the Atlantic Ocean, where layers of ice-rafted debris tell the story of massive iceberg armadas that shouldn't have existed. You find it in the pollen records from European peat bogs, showing vegetation communities that assembled, thrived, and collapsed in the geological equivalent of an eye blink. You find it in the cave formations of China, in the lake beds of East Africa, in the coral reefs that grew and died in the Western Pacific. In a cramped office at Columbia University's Lamont Doherty Earth Observatory, you meet Dr. Wallace Broecker, the man who coined the term global warming back in 1975. Though he's far more interested in talking about something else, the ocean's conveyor belt. This is what scientists call the thermohaline circulation, a vast system of currents that moves heat around the planet like blood through a body. Warm water flows north in the Atlantic, cools, becomes denser, sinks, and returns. South in the deep ocean. It's been doing this for so long that we've built entire civilizations assuming it always will. Broecker shows you data suggesting that this circulation system has an Achilles heel. When too much fresh water enters the North Atlantic, from melting ice sheets for instance, the water doesn't become dense enough to sink. The conveyor belt slows. Then it stops. And when it stops, the climate system doesn't gradually adjust. It lurches into a new configuration like a switch being flipped. The Younger Dryas period, that cold snap that ended so abruptly 11,700 years ago, appears to have been triggered by exactly this mechanism. As the great ice sheets of North America melted at the end of the last ice age, they created vast lakes of meltwater. Lake Agassiz, centered over what is now Manitoba, contained more water than all of today's Great Lakes combined. Then, around 12,900 years ago, something happened, possibly the collapse of an ice dam, and this enormous volume of fresh water catastrophically drained into the North Atlantic. The conveyor belt shut down. Temperatures in the northern hemisphere plummeted, even as the planet overall was warming. Europe found itself in the grip of near glacial conditions. The forests that had begun to return gave way to tundra, and the people who had started to settle down to experiment with cultivating wild grains found their nascent agricultural experiments threatened by a climate that had turned hostile with startling speed. But you're not here just to learn about what happened 12,000 years ago. You're here because of what's happening now and what might be about to happen. As you sit in these laboratories and archives, reading papers with titles like Persistent North Atlantic Meridional Overturning Circulation Weakening and Greenland Ice Sheet Mass Balance Accelerating Loss in the 21st Century, you begin to understand why a small but growing group of scientists are deeply concerned. The Greenland ice sheet is currently losing approximately 280 billion tons of ice per year. This isn't a gradual melting, it's accelerating. The meltwater is flowing into the North Atlantic, creating a pool of fresher, less dense water exactly where the ocean's conveyor belt is supposed to sink and circulate. Measurements of the Atlantic meridional overturning circulation, the formal name for Brocker's conveyor belt, show that it has already weakened by about 15% since the mid-20th century. You find yourself in conversation with Dr. Stefan Rahmstorf at the Potsdam Institute for Climate Impact Research in Germany. He spent years analyzing ocean temperature and salinity data, and his conclusions are presented with the careful hedging of a scientist who knows how easily such statements can be sensationalized, but his concern is evident. The current weakening of the circulation, he explains, is happening faster than most climate models predicted. Not catastrophically fast, not yet, but fast. Enough that the possibility of a threshold being crossed, of the system shifting into a new state, cannot be dismissed. The question hanging in the air, unspoken but present in every conversation and every paper you read, is this: are we approaching another one of those transitions? Are we, through our additions of greenhouse gases to the atmosphere and the resulting ice melt, inadvertently recreating the conditions that triggered past climate upheavals? The 12,000-year cycle isn't a law of nature, not in the way that gravity is. It's an observed pattern, a rhythm in the Earth's climate system that appears to be tied to the waxing and waning of ice ages, to orbital mechanics, to the complex feedbacks between ocean, atmosphere, and ice. But it's also disturbingly regular. The Younger Dryas began around 12,900 years ago. The Holocene, our current warm period, began around 11,700 years ago, which means we're now 11,700 years into what might be a 12,000-year cycle. In the ice cores, you can see other such transitions. There was one approximately 23,000 years ago, another around 35,000 years ago, another around 47,000 years ago. The precise timing varies, the triggers differ, but the pattern of abrupt change recurs with unsettling regularity. And in nearly every case, these transitions involve dramatic reorganizations of the ocean circulation, massive releases of fresh water into the ocean, and climate shifts that reshaped ecosystems across the globe. You spend an afternoon in the archives of the Woods Hole Oceanographic Institution, poring over sediment cores taken from the seafloor off the coast of Portugal. These cores contain evidence of something called Heinrich events, episodes during the last ice age when vast armadas of icebergs were released into the North Atlantic, carrying with them rocks and debris that settled to the ocean floor as the ice melted. These events occurred roughly every 7,000 to 10,000 years during the last glacial period, and each one corresponded with significant climate disruptions. The mechanism behind Heinrich events is still debated, but the leading theory involves an instability in ice sheets. As ice accumulates, it insulates the bedrock beneath it. The pressure and insulation cause the base of the ice sheet to warm until it begins to melt. This creates a layer of water that lubricates the ice sheet's base, allowing massive sections to slide into the ocean. It's a self-regulating cycle, but one with dramatic consequences. Could something similar happen with today's ice sheets? The West Antarctic ice sheet sits partially below sea level, grounded on bedrock but vulnerable to warm ocean currents undermining it from below. Glaciologists have identified several glaciers in West Antarctica that appear to have already crossed a threshold into irreversible retreat. The Pine Island and Thwaites glaciers are losing ice at accelerating rates, and computer models suggest that their collapse could be impossible to prevent. Even if we stopped all greenhouse gas emissions tomorrow, if the West Antarctic ice sheet were to collapse, a process that would take centuries, but which may have already begun, it would add roughly 3.3 meters, about 11 feet, to global sea levels. That's not the catastrophic part, though it would certainly be catastrophic enough for coastal cities. The catastrophic part is what all that fresh water entering the Southern Ocean might do to global ocean circulation patterns. You find yourself thinking about cycles within cycles. The Milankovitch cycles, variations in Earth's orbit, and axial tilt that occur over tens of thousands of years, are well established as pacing mechanisms for ice ages. But within those long cycles, there are shorter rhythms, faster oscillations. The climate system seems to have multiple time scales on which it operates, from the annual cycle of seasons to the decades-long cycles of ocean oscillations like El Niño, to these millennial-scale reorganizations that remake the world. And yet in all the ice core data, in all the sediment records and pollen cores and cave formations, there's no precedent for what we're doing now. Never in the past million years has the atmospheric concentration of CO2 risen as rapidly as it has in the past century. Never has so much heat been added to the ocean so quickly. We are, in effect, conducting an experiment on the Earth's climate system, pushing it in ways it has never been pushed before, and wondering whether we might inadvertently trigger one of those abrupt reorganizations that the paleoclimate record shows are not just possible, but seemingly inevitable, given enough time and the right conditions. In a quiet moment, sitting in a library with a stack of scientific papers before you, you come across a curious detail. Many ancient cultures have flood myths, stories of a great deluge that reshaped the world. The Epic of Gilgamesh, the story of Noah, Hindu texts describing Manu and the Great Flood, Chinese legends of Gun Yu taming the waters. They appear across cultures that had no contact with one another. For a long time, these were dismissed as either independent inventions or evidence of diffusion from a single source. But the timing is interesting. Many of these myths, when analyzed by scholars, seem to contain elements that might be cultural memories of real events dating back to the end of the last ice age. The Younger Dryas period and its abrupt ending coincide roughly with the rise of agriculture and the first permanent settlements. It was a time when rising sea levels inundated vast coastal plains, areas where many humans likely lived, as coastlines have always been preferred settlement sites. The Persian Gulf was dry land 12,000 years ago. So was the floor of the Black Sea. Both flooded relatively quickly as ice melted and sea levels rose. Could these myths be garbled memories passed down through countless generations of a time when the climate changed with a speed that must have seemed supernatural to the people experiencing it? When the rains came or stopped coming, when the seas rose, when the world they knew was transformed? And if so, what myths might future generations tell about our time? The question sits there, in the data and the ice cores and the careful scientific papers, waiting. The 12,000-year cycle isn't a prophecy, not in any mystical sense. It's a pattern observed in natural records, a tendency of the Earth's climate system to undergo periodic reorganizations. But patterns have a way of repeating, and we are now, through our own actions, creating conditions that look disturbingly similar to those that preceded past transitions. The ice continues to melt. The fresh water continues to flow into the North Atlantic. The circulation continues to weaken, and in laboratories around the world, scientists continue to watch and measure and model, trying to answer a question that becomes more urgent with each passing year. How close are we to the edge? How much can we push before the system pushes back? You leave the laboratory as the sun sets, the ice core samples safely return to their frozen storage. Outside, the world seems ordinary, stable, unchanging. But you carry with you the knowledge of what lies hidden in those cores, a record of change so rapid and so complete that it challenges everything we think we know about the stability of the world we've built our civilization upon. And you wonder, if it happened before, if it's happened repeatedly throughout Earth's history, what makes us think it won't happen again? The scientists don't have a definitive answer. They have probabilities, scenarios, models that range from gradual change to abrupt catastrophe. But lurking in all of it is the uncomfortable truth that the paleoclimate record reveals. The Earth's climate system has a history of surprises, and not the pleasant kind. It has thresholds and tipping points, and once crossed, there may be no going back. As you drive away, you think about those ancient peoples watching their world transform, helpless to stop it, not understanding why it was happening. And you wonder if, despite all our science and technology, we might be about to learn what they learned, that some forces are larger than us, that some changes once begun cannot be stopped, and that the line between the world we know and a world transformed can be crossed far more quickly than we ever imagined possible. The cycle continues its slow turn, and we are, perhaps, approaching another revolution. But unlike our ancestors, we have been warned. The question is whether we'll heed that warning before it's too late, or whether future researchers will study our time in ice cores yet to be frozen, wondering why we didn't act when we could. You're standing on a beach in what is now the Persian Gulf, except there is no Gulf. It's 14,000 years ago, and what will one day be seafloor is now a verdant river valley, a place where fresh water flows, and vegetation flourishes in an otherwise arid landscape. Archaeological evidence, when you return to the present, will be scarce. Most of it now lies under 300 feet of water. But what little has been found suggests this was a place where people gathered, where some of the earliest experiments in settling down, in staying in one place rather than following the herds, might have occurred. The people here don't know they're living on borrowed time. They don't know that far to the north, enormous ice sheets are beginning to collapse, that meltwater is pooling in vast lakes behind ice dams, that the sea level is rising at a rate that will eventually be measured at roughly 1 meter per century, slow by modern standards, but fast enough that a person born here might, in their lifetime, notice the salt water creeping inland. But that's the gradual change, the predictable shift. What they really don't know is that the climate system is about to do something unexpected, something that will make those slowly rising seas seem trivial by comparison. In less than a generation, the younger dryas will begin, and the world they know will be transformed. Dr. Jeffrey Rose, an archaeologist who has spent years studying the drowned landscapes of the Persian Gulf, has proposed something he calls the Gulf Oasis hypothesis, based on the limited evidence available, ancient river channels mapped with sonar, a few artifacts dredged up from what is now seafloor, and extrapolations from sites just beyond the current coastline. He suggests that this region might have been a crucial refugium during the last ice age, a place where conditions remained relatively favorable, even as much of the world was locked in ice. When you examine the timeline, something interesting emerges. The Persian Gulf didn't fully flood until around 8,000 years ago, much later than the initial post-glacial sea level rise. But the process began earlier, and it accelerated during the rapid warming at the end of the Younger Dryas. If people were living in this drowned valley, and the circumstantial evidence suggests they would have experienced a slow-motion catastrophe, their world literally shrinking beneath them as the seas advanced. Where did they go? Some likely moved inland, up into the Mesopotamian plain, and it's here that the speculation becomes tantalizing, if unprovable. The oldest permanent settlements in Mesopotamia appear shortly after the Gulf would have begun flooding. The earliest irrigation systems, the first large-scale agricultural communities, the initial experiments with social organization beyond the family or tribe, they all emerge in this region during this time period. Is it coincidence? Perhaps. Or perhaps the flooding of the Gulf Oasis, the loss of a homeland that had sustained populations for thousands of years, provided the impetus for new ways of living. When you can no longer rely on the old places, the old patterns, you must innovate or perish. The people who fled the rising waters brought with them knowledge, experience, and a necessity. They had to make new places work, had to develop new strategies for survival. You find similar patterns around the world. In Britain, Doggerland, a vast plain connecting what is now the UK to continental Europe, was progressively drowned as sea levels rose. Doggerland wasn't empty. Archaeological evidence from the few areas not now underwater shows it was a rich hunting ground, possibly home to thousands of people. By 6,500 years ago, it was gone, reduced to a few islands before those too were swallowed. The people of Doggerland didn't simply vanish. They moved, adapted, changed, but they also lost something irreplaceable. A homeland, a landscape that held generations of knowledge about where to hunt, where to gather, where to find shelter. All of that accumulated wisdom became useless as the land disappeared beneath the waves. In the library of the University of California, Santa Barbara, you find the work of Dr. John Erlandson, an archaeologist specializing in coastal sites. He spent his career fighting against what he calls the tyranny of the present shoreline, the assumption that ancient peoples lived where we can easily find their remains. In fact, he argues, humans have always been drawn to coasts, and during the Ice Ages, when sea levels were 120 meters, nearly 400 feet, lower than today, the coastlines were far different than what we see now. The richest archaeological sites, the places where the most people lived and where the most cultural development occurred, are now underwater. We're studying the periphery, the margins, and assuming that's where the center was. It would be like future archaeologists studying our civilization based only on mountain communities, having missed entirely the existence of coastal cities because they're now submerged. Erlandson has documented sites along the California coast that were clearly major settlements, places where people returned generation after generation. But these sites are anomalies, preserved only because they were on elevated points that remained above the rising seas. For every site we've found, there might be dozens or hundreds that are now underwater, their stories lost. This matters because it means our understanding of human development, of when and how we transition from mobile hunter-gatherers to settled farmers, might be fundamentally skewed. We're missing data from the very places where those transitions might first have occurred. The agricultural revolution might not have been as sudden as it appears in our archaeological record. It might be sudden only because we can't see its earlier stages, which are now submerged. But there's another implication, one that's relevant to our current situation. If major cultural developments occurred in precisely those areas most vulnerable to sea level rise, and if those areas were subsequently inundated, then human civilization has already experienced the loss of significant populations and knowledge bases to rising seas. It's happened before, and it could happen again. Modern sea level rise is currently proceeding at about 3.3 millimeters per year, which sounds trivial until you calculate that over a century. That's 33 centimeters, about a foot. But that's just the current rate. It's accelerating. Some projections suggest we could see a meter or more of sea level rise by 2100 and several meters by 2300 if current trends continue. This wouldn't just inconvenience coastal cities. It would fundamentally redraw the map of human civilization. Consider, roughly 40% of humanity currently lives within 100 kilometers of a coast. In many countries, that percentage is much higher. The Netherlands, Bangladesh, Pacific Island nations, major cities from New York to Shanghai to Mumbai, all would face existential challenges. But here's where the 12,000-year cycle becomes relevant again. The sea level rise we're experiencing now is partly a continuation of natural post-glacial processes, but it's been enormously accelerated by anthropogenic warming. And if we trigger an abrupt climate shift, if the ocean circulation changes, if major ice sheets collapse faster than predicted, the sea level rise could accelerate further, possibly dramatically. During the early Holocene, there were periods when sea levels rose at rates of up to 40 millimeters per year, more than 10 times the current rate. These rapid rises were associated with massive ice sheet collapses, events that dumped enormous volumes of water into the oceans over relatively short periods. The geological evidence suggests these weren't smooth, gradual processes, but rather step-like, with periods of relative stability punctuated by sudden jumps. Could it happen again? The West Antarctic ice sheet, as mentioned, is already showing signs of instability, but there's also concern about the Greenland ice sheet and parts of East Antarctica. Together, these ice sheets contain enough water to raise global sea levels by more than 60 meters. Obviously, they won't all melt tomorrow or even in the next few centuries under most scenarios, but they don't need to melt completely to cause catastrophic problems. A partial collapse of just the West Antarctic ice sheet, combined with accelerated melting in Greenland, could raise sea levels by 4 to 5 meters. That would be enough to redraw the world map, displacing hundreds of millions of people and submerging trillions of dollars of infrastructure. And unlike our ancestors on the shores of the rising Persian Gulf, who could move inland to relatively empty lands, where would modern populations go? Every habitable place on Earth is already claimed, already occupied. Climate refugees in the tens or hundreds of millions would overwhelm any existing frameworks for managing migration. The social, political, and economic disruptions would be profound. You meet with Dr. Andrea Dutton, a geologist who studies past sea levels to understand future risks. She shows you evidence from the last interglacial period, roughly 125,000 years ago, when global temperatures were only slightly warmer than today, perhaps 1-2 degrees Celsius warmer. Sea levels during that period stabilized at 6 to 9 meters higher than present. There were no ice sheets to speak of in the northern hemisphere. Greenland had lost a significant portion of its ice, and West Antarctica had likely collapsed. The disturbing part is that we're now approaching similar temperature conditions, and we're doing so much faster than the Earth warmed 125,000 years ago. The ice sheets haven't caught up yet. Ice moves slowly, but they will. The sea level rise we've experienced so far, about 20 centimeters since 1900, is just the beginning. We've committed to much more, even if we stopped all emissions today, simply because the ice sheets are responding to warming that's already occurred. Dutton speaks carefully, as scientists do, about uncertainty ranges and confidence levels. But the core message is clear. We know from the paleoclimate record that ice sheets can collapse. We know that sea levels can rise by meters over periods of centuries. We know that the warming we've caused puts us on a trajectory toward those conditions. What we don't know precisely is the timing, how fast it will happen, whether it will be gradual or punctuated by sudden accelerations. But there's a deeper question lurking beneath the science, one that touches on the 12,000-year cycle and our place within it. Are we simply experiencing natural variability, a continuation of processes that have been ongoing since the last ice age ended? Or have we, through our emissions of greenhouse gases, fundamentally altered the trajectory, possibly triggering changes that wouldn't otherwise have occurred for thousands more years? The evidence suggests the latter. While sea levels were still slowly rising from residual ice sheet melting, they had largely stabilized over the past few thousand years. The Holocene, our current interglacial period, has been remarkably stable compared to previous interglacials. That stability is likely one reason why human civilization was able to develop as it did. But we've now pushed CO2 levels far beyond anything experienced during the Holocene. And we're warming the planet to temperatures not seen since the Eemian interglacial 125,000 years ago. In effect, we're not just experiencing a natural cycle. We're forcing the climate system into conditions it hasn't seen in over 100,000 years. And we're doing it at a speed that's unprecedented in the geological record, except during the most catastrophic events. Volcanic eruptions, asteroid impacts, and yes, those abrupt climate transitions that mark the end of one era and the beginning of another. The prophecy, if we can call it that, isn't written in ancient texts. It's written in ice cores and sediments, in the fossil record of coral reefs, and the isotope ratios preserved in cave formations. It's a prophecy that says the Earth's climate system has done this before, many times, and it can do it again. And when it happens, it doesn't ask permission, doesn't give warnings beyond what we're capable of reading in the geological record. It simply shifts, reorganizes, finds a new equilibrium that might be radically different from what came before. Standing on that imaginary beach in the Persian Gulf 14,000 years ago, watching the sun set over a landscape that would soon be lost forever, you wonder what those ancient people thought as they noticed the changes. Did they understand what was happening? Did they try to fight it, building barriers against the rising water? Or did they simply accept it as the will of forces beyond their control and move on, carrying with them only what they could save, their knowledge, their stories, their determination to survive? We have advantages they didn't. We understand the mechanisms driving the changes. We have the technology to model future scenarios, to measure the ice sheets and ocean currents with precision. We can, in theory, take actions to mitigate the worst outcomes, to slow or even potentially reverse some of the changes. But we also have disadvantages. Our civilization is far more complex, more interconnected, more dependent on specific infrastructure and stable conditions. We've built our cities in precisely the places most vulnerable to sea level rise. We've created global supply chains that assume reliable shipping routes and stable coastal ports. We've organized our food production systems around climate patterns that are now shifting. We have, in short, made ourselves exquisitely vulnerable to precisely the kind of changes that the paleoclimate record shows are not only possible, but given enough time, inevitable. The question isn't whether the climate will change. It always has and always will. The question is whether we'll manage that change intelligently, with foresight and planning, or whether we'll stumble into it blindly, forced to react to crises as they emerge. And underlying that question is another. Have we already set in motion changes that we can no longer prevent, committed ourselves to a future that, while not as dramatic as the prophecies of ancient seers, will nonetheless reshape human civilization as profoundly as those ancient climate shifts reshaped the world of our ancestors? The data doesn't provide easy answers, but it does provide context, a longer view that should temper both complacency and panic. We are not the first humans to face dramatic environmental change. We likely won't be the last, but we are the first to face such change with full knowledge of what's coming, with the tools to understand and potentially moderate it. Whether that knowledge will prove to be advantage enough remains to be seen. The cycle turns, the ice melts, the seas rise, and we, like countless generations before us, must adapt or face the consequences. You're standing in a laboratory at the University of Tokyo, watching a technician carefully position a small sample of volcanic rock beneath a highly sensitive magnetometer. The rock is from Mount Fuji, dated to approximately 12,800 years ago, right around the beginning of the Younger Dryas. But the researchers here aren't particularly interested in the Younger Dryas itself. They're interested in what the rock remembers about something else entirely, the Earth's magnetic field. Every volcanic rock is, in a sense, a frozen compass. When lava cools and solidifies, magnetic minerals within it align themselves with the Earth's magnetic field, creating a permanent record of that field's direction and intensity at the moment of cooling. By studying rocks of different ages from locations around the world, scientists have been able to reconstruct the history of Earth's magnetic field going back millions of years. And what they've found is both fascinating and, to some researchers, deeply concerning. The Earth's magnetic field is not stable. It wanders, weakens, strengthens, and occasionally, roughly every 200,000 to 300,000 years on average, it flips entirely, with north and south magnetic poles swapping places. We know this has happened hundreds of times in Earth's history. The last complete reversal, the Brunhes-Matuyama reversal, occurred about 780,000 years ago. We're overdue for another one, at least by average standards, though overdue in geological terms doesn't mean much. The next reversal could be tomorrow or 100,000 years from now. But there's something else in the magnetic record, something that operates on a different time scale and which has only recently begun to receive serious attention. The field doesn't just reverse. It also exhibits shorter-term variations, periods where it weakens significantly without fully reversing. These excursions, as they're called, can last anywhere from a few centuries to a few thousand years, and during them, the magnetic field can drop to as little as 10% of its normal strength. Dr. Yusuke Yokoyama, the lead researcher on the project you're observing, has spent years studying one such excursion. It's called the Lachamp event, and it occurred approximately 41,000 years ago. For about 500 years, the Earth's magnetic field nearly collapsed, dropping to less than 25% of its current strength. The magnetic poles wandered dramatically during this period, and cosmic radiation reaching Earth's surface increased substantially. What makes Yokoyama's work particularly interesting is what else he's found in the geological record from this time. The Lachamp event coincides with significant climate fluctuations, changes in atmospheric circulation patterns, and, perhaps most intriguingly, major shifts in human behavior and culture. Around 42,000 years ago, Neanderthals went extinct in their last refugia. Cave art suddenly proliferated. Large fauna in Australia experienced a wave of extinctions. The timing might be coincidental, but it's suggestive enough that several researchers are now seriously investigating whether geomagnetic excursions might have broader impacts than previously thought. But you're not here to study the Lachamp event. You're here because Yokoyama and his colleagues have identified evidence of another excursion, one that's received far less attention, the Gothenburg excursion, dated to approximately 2,500 years ago, right at the height of the Younger Dryas. The evidence for the Gothenburg excursion is less definitive than for Lachamp. The signal is weaker, the global distribution of confirming data is spottier. But multiple studies have now identified anomalies in the magnetic record from this period, suggesting that the Earth's magnetic field weakened substantially, though probably not as dramatically as during Lachamp. Sediment cores from Swedish lakes, hence the name Gothenburg, volcanic rocks from Iceland, and marine sediments from the Pacific all show similar signatures. A period of magnetic instability centered on 12,500 years ago, lasting perhaps a few hundred years. Now, the Earth's magnetic field does not, as far as we understand, directly cause climate change. The magnetic field shields us from cosmic radiation and helps prevent the solar wind from stripping away our atmosphere, but it doesn't regulate temperature or precipitation patterns. However, there are several mechanisms through which a weakened magnetic field might influence climate, and these mechanisms are now being actively researched. One hypothesis involves cosmic rays. When the magnetic field weakens, more cosmic rays penetrate Earth's atmosphere. These high-energy particles can ionize atmospheric gases, potentially influencing cloud formation. The theory, still controversial and not fully accepted, is that increased cosmic radiation could lead to increased cloud cover, which in turn could influence global temperatures. The exact mechanisms and magnitudes of these effects are debated, but laboratory experiments and satellite observations have confirmed that cosmic rays can indeed affect atmospheric chemistry. Another mechanism involves the ozone layer. Cosmic radiation can break down ozone molecules, and during geomagnetic excursions, this destruction could intensify, potentially allowing more UV radiation to reach the surface. Increased UV radiation could affect ecosystems, particularly in the oceans where phytoplankton, the base of the marine food chain, are vulnerable to UV damage. Changes in ocean ecosystems could, through complex feedbacks, influence carbon cycling and climate. A third mechanism, even more speculative, involves the solar wind. The Earth's magnetic field normally deflects most of the charged particles streaming from the sun. During a geomagnetic excursion, more of these particles could penetrate into the upper atmosphere, potentially affecting atmospheric chemistry and circulation patterns in ways we're only beginning to understand. Yokoyama shows you data that's particularly intriguing: ice core records of beryllium-10, a cosmogenic isotope produced when cosmic rays strike the atmosphere. The beryllium-10 levels spike around 12,500 years ago, confirming that cosmic radiation did indeed increase during this period. The spike isn't as dramatic as the one seen during the Lachamp event, but it's there, a clear signature of reduced magnetic shielding. Could this have influenced the Younger Dryas climate? Yokoyama is cautious about claiming a direct link. The timing is right, but correlation doesn't prove causation, and there are other more accepted explanations for the Younger Dryas involving meltwater pulses and ocean circulation changes. But he does note that the two explanations aren't mutually exclusive. Perhaps the geomagnetic excursion was a contributing factor, an additional stress on a climate system already being disrupted by melting ice sheets. You spend an afternoon reviewing studies that have attempted to model the climate impacts of geomagnetic excursions. The models are crude, there's so much uncertainty about the mechanisms involved, but they generally suggest that significant magnetic field weakening could produce regional climate anomalies, particularly in the polar regions where the magnetic field lines converge and where cosmic radiation effects would be strongest. Interestingly, some models predict that a weakened magnetic field could lead to a cooling effect in the northern hemisphere through increased cloud cover and changes in atmospheric circulation. If true, this could have amplified the cooling caused by the shutdown of the Atlantic circulation during the Younger Dryas. Two separate mechanisms, one involving ocean currents and one involving the magnetic field, working together to produce a climate shift more severe than either could have caused alone. But there's another aspect to this story, one that brings us back to the 12,000-year cycle. You discover that geomagnetic excursions are not randomly distributed in time. While they don't occur on a strict cycle, there are patterns. Analysis of the paleomagnetic record shows clustering of excursions and reversals during certain periods, and some researchers have suggested links to external factors such as changes in the Earth's core dynamics, which might themselves be influenced by patterns in the Earth's orbit or even by the solar system's movement through the galaxy. Dr. Brad Clement at Florida International University has compiled one of the most comprehensive databases of paleomagnetic variations spanning the last 100,000 years. When you examine his work, a curious pattern emerges. Geomagnetic excursions and periods of rapid field change appear more frequently during times of major climate transitions, during deglaciation periods, during the boundaries between glacial and interglacial states, during times when the Earth's climate system is already under stress from other factors. Is this meaningful, or is it simply that these are the periods we study most intensively, making us more likely to notice magnetic anomalies? Clement admits the data is still too sparse to draw firm conclusions, but he points out that there may be a physical connection. The Earth's core, where the magnetic field is generated, doesn't exist in isolation. It's thermally coupled to the mantle above it, and there's evidence that major changes in surface ice loading, the immense weight of ice sheets growing and shrinking, can influence mantle convection patterns, which in turn might affect core dynamics. Think about it. During the last ice age, you had ice sheets kilometers thick covering much of North America and Eurasia. This represented an enormous redistribution of mass on Earth's surface. As the ice accumulated, the crust beneath it was pressed down, displaced mantle material, and changed the planet's moment of inertia, literally altered how it spins. When the ice melted, the crust rebounded, mass redistributed again, and the entire system had to readjust. Could these massive surface changes influence the dynamo process in the core that generates the magnetic field? Most geophysicists would have said no until recently. The core is too deep, too isolated, too governed by its own internal processes. But newer models that couple core dynamics with mantle convection suggest the answer might be more complex. Changes in mantle convection driven by surface mass redistribution or by other factors could potentially influence the flow patterns in the outer core, and those flow patterns are what generate the magnetic field. If this connection exists, it would mean that periods of major climate change, specifically the transitions between glacial and interglacial states, might be correlated with increased likelihood of geomagnetic instability. Not because one causes the other directly, but because both are responding to the same deeper planetary processes, the same shifts in how energy and mass are distributed within the Earth system. And this brings you to an uncomfortable realization. We're currently in one of those transition periods. We're at the tail end of the Ice Age cycle, in a warm interglacial period, but one that we've now artificially extended and intensified through greenhouse gas emissions. We're also experiencing a significant weakening of the Earth's magnetic field. It has declined by about 9% over the past 170 years, according to direct measurements, and the rate of decline is accelerating in some regions. The South Atlantic anomaly, a region where the magnetic field is particularly weak, has been growing and intensifying. Satellites passing through this region experience higher rates of electronic malfunctions due to increased radiation exposure. The magnetic North Pole has been wandering more rapidly in recent years, moving from the Canadian Arctic towards Siberia at a rate of about 55 kilometers per year, much faster than the historical average of 10 to 15 kilometers per year. Are these signs of an impending geomagnetic reversal or excursion? You attend a conference in Kyoto where this exact question is debated. The consensus is maybe, but we can't be sure. The instrumental record of the magnetic field only goes back a few centuries, a geological eye blink. We don't know what normal variability looks like on longer timescales. The field might recover its strength without any major excursion occurring. Or we might be in the early stages of a process that will take centuries or millennia to fully unfold. But several researchers at the conference present work suggesting we should take the possibility seriously. Dr. Monika Korte from the GFZ German Research Center for Geosciences shows reconstructions of the magnetic field over the past 100,000 years based on archaeological artifacts, lava flows, and sediment cores. The current rate of field weakening, she notes, is not unprecedented, but it is unusual. Similar rates of change in the past have sometimes, not always, but sometimes preceded major excursions or reversals. More concerning is work presented by Dr. Richard Holm from the University of Liverpool. He's been studying what are called geomagnetic jerks, sudden changes in the rate at which the magnetic field is changing. These jerks, which occur every few years to every few decades, are thought to represent changes in the flow patterns in the Earth's outer core. Holm has identified an increasing frequency and intensity of these jerks over the past few decades, suggesting that the core's dynamo is becoming more turbulent, more unstable. Could this instability trigger an excursion in the near future? Near future by geological standards, meaning the next few centuries. It's possible. And if it does, what would the consequences be? The direct effects of a geomagnetic excursion on human health are probably minimal. The increased cosmic radiation would be a problem for satellites, for astronauts, for air travel at high altitudes and latitudes, but at ground level, the atmosphere provides substantial shielding. You might see increased cancer rates from elevated UV exposure if the ozone layer is significantly damaged, but this would likely be a small increase, not a civilization-threatening catastrophe. The indirect effects, however, could be more serious. Our technological civilization is deeply dependent on satellites for communication, navigation, weather forecasting, military applications, financial systems, and more. A severely weakened magnetic field would expose these satellites to much higher radiation levels, potentially degrading their electronics and shortening their operational lifetimes. The South Atlantic anomaly already causes problems. Imagine if that anomaly expanded to cover much of the planet. Power grids are another vulnerability. While a geomagnetic excursion isn't the same as a solar storm, it could make the Earth more vulnerable to solar activity. The magnetic field normally deflects much of the charged particle radiation from solar flares and coronal mass ejections. With a weakened field, more of this energy could penetrate to the Earth's surface, inducing electrical currents in long-distance power lines and potentially causing blackouts. The 1859 Carrington event, a massive solar storm that occurred when the magnetic field was at normal strength, caused telegraph systems to fail across North America and Europe. A similar event today, with a weakened magnetic field, could be catastrophic for our electrical infrastructure. But you're also interested in the climate implications, and this is where the research becomes more speculative and controversial. You find a handful of papers suggesting that geomagnetic excursions might have influenced past climate transitions. The mechanisms are uncertain, probably involving cosmic rays, cloud formation, and ozone layer changes, but the timing correlations are sometimes striking. One particularly provocative study, published in Science in 2021, examined the Lachamp excursion in detail using tree ring radiocarbon records, ice cores, and climate proxies. The authors found evidence that the period of minimum magnetic field strength coincided with significant climate anomalies, shifts in monsoon patterns, changes in wind systems, and alterations in atmospheric circulation. They proposed that the increased cosmic radiation during the excursion affected atmospheric chemistry in ways that influenced climate, and they noted that the effects were not uniformly distributed globally. Some regions experienced cooling, others warming, depending on how regional circulation patterns shifted. Could something similar have happened during the Gothenburg excursion, the one that coincides with the Younger Dryas? You find a few papers that explore this possibility, but the evidence is thin. The Gothenburg excursion was less intense than Lachamp, so any climate effects would presumably be smaller. And disentangling potential magnetic field effects from the much larger effects of the meltwater pulse and ocean circulation shutdown is nearly impossible with current data. But here's what keeps some researchers awake at night. We might be about to run a natural experiment. If the Earth's magnetic field continues to weaken, if we do enter a geomagnetic excursion within the next few centuries, we'll experience it during a time of unprecedented anthropogenic climate change. We'll have two major perturbations to the climate system happening simultaneously, greenhouse warming and potential magnetic field effects, and trying to separate their influences will be extraordinarily difficult. Worse, they might interact in unexpected ways. Climate models don't currently include geomagnetic field variations because the mechanisms linking them to climate are so poorly understood. If those mechanisms turn out to be significant, our projections for future climate change could be missing an important component. You spend an evening reading through the paleoclimate literature, looking for other instances where geomagnetic excursions coincided with climate shifts. The correlations are tantalizing but frustratingly ambiguous. Around 41,000 years ago, the Lachamp event coincided with a cold period in the northern hemisphere. Around 34,000 years ago, another possible excursion coincides with another cold snap. Around 23,000 years ago, during the last glacial maximum, there are magnetic field anomalies that correlate with shifts in ice sheet dynamics. But correlation isn't causation, and the magnetic field is not the only thing changing during these periods. The Earth's orbit is slowly varying due to gravitational interactions with other planets. These Milankovitch cycles influence the distribution of solar radiation reaching Earth's surface. Solar output itself varies on multiple time scales. Ocean circulation patterns shift. Volcanic activity waxes and wanes. Trying to isolate the effect of magnetic field changes from all these other variables is extraordinarily difficult. Yet the pattern persists. Every 10,000 to 15,000 years, give or take, you see evidence of both geomagnetic instability and climate disruption. The timing isn't exact, it's not a strict cycle, but it's regular enough to suggest some underlying connection, some deeper rhythm in the Earth system that we're only beginning to recognize. And we're right at the point in time where if the pattern holds, we might expect another such event. It's been approximately 12,000 years since the Gothenburg excursion and the Younger Dryas. It's been 41,000 years since Lachamp. If there's a 12,000-year component to geomagnetic variability, we're due. If there's a 41,000-year component, which would align with one of the Milankovitch orbital cycles, we've got time. But the magnetic field is already weakening faster than it has in thousands of years, and we don't know what that means. Dr. Gauthier Hulot at the Institute of Earth Physics in Paris has developed models of the geodynamo, the process that generates Earth's magnetic field, that can reproduce some of the observed behavior, including excursions and reversals. When you examine his work, one thing becomes clear: the system is inherently chaotic. Small changes in initial conditions can lead to dramatically different outcomes. The Earth's core, a sphere of molten iron spinning and convecting, is a turbulent, unpredictable system, and while we can identify general patterns and tendencies, predicting exactly what it will do next is beyond our current capabilities. This uncertainty is deeply frustrating for both scientists and policymakers. We can say that a geomagnetic excursion is possible, even perhaps likely within the next few centuries. We can say that such an excursion could have consequences for climate, for technology, for human society, but we can't say when it will happen, how severe it will be, or exactly what the impacts will be. We're dealing with probabilities and scenarios, not certainties, and yet the paleomagnetic record suggests we ignore this at our peril. The Earth's magnetic field has undergone major changes many times in the past, and at least some of those changes appear to have coincided with significant disruptions to climate and ecosystems. Whether the magnetic changes caused the disruptions were caused by the same underlying factors that caused the disruptions, or simply happened to occur at the same time, by coincidence remains unclear, but the possibility that they're connected, that the 12,000-year cycle of climate upheaval might be linked to a similar cycle of geomagnetic instability, is one that's beginning to receive serious scientific attention. You leave Tokyo with a head full of data and uncertainties. On the flight back, you watch the airplane's navigation system, which relies on GPS satellites, which in turn rely on the Earth's magnetic field for some of their corrections and calibrations. You think about how fragile our technological infrastructure is, how dependent on invisible fields and forces that we take for granted, but which are actually dynamic, changing, potentially unreliable on long time scales. And you think about those ancient peoples watching the auroras spread to latitudes where they'd never been seen before, as would happen during a geomagnetic excursion when the weakened field allows charged particles to penetrate deeper into the atmosphere. Did they see these lights in the sky as omens, as warnings? And if so, warnings of what? They couldn't have understood the mechanisms, but perhaps they understood intuitively what the data now suggests, that when the heavens themselves are disturbed, when the fixed patterns of nature begin to shift, other changes of climate, of environment, of the very stability of the world may follow. The magnetic memory recorded in rocks tells us that our planet is not as stable as we assume. The field that shields us, that makes navigation possible, that helps hold our atmosphere in place against the solar wind, is itself subject to dramatic variations. And if those variations are somehow coupled to the other cycles that govern Earth's climate, if they're part of the same system of interactions that produces the 12,000-year rhythm of change, then we need to understand them far better than we currently do. Because unlike our ancestors, we've built a global civilization that depends on stability. We've engineered systems that require predictability. We've grown accustomed to the idea that the fundamental forces of nature are constant. But the rocks remember otherwise. They remember chaos, change, and transformation. And they whisper a warning we would be wise to heed. The earth has its own cycles, its own rhythms, and they care nothing for human convenience or human plans. You're examining a thin slice of ice under polarized light in a laboratory at the University of Copenhagen. The ice is from the Neem Core, North Greenland Eemian ice drilling, and it's approximately 128,000 years old, from the last interglacial period before our own. But you're not looking at the ice itself. You're looking at what's trapped within it. Dust. The dust appears as tiny, dark inclusions, each particle a microscopic time capsule carrying information about conditions on Earth's surface more than 100,000 years ago. Under an electron microscope, these particles reveal their origins: minerals from Asian deserts, volcanic ash from eruptions half a world away, even cosmic dust from meteors burning up in the atmosphere. Each type of dust has a signature, a characteristic composition that allows researchers to trace it back to its source. Dr. Paul Vallelonga, the glaciologist showing you these samples, explains that dust in ice cores is one of the most informative climate proxies available. The amount of dust tells you how dry and windy conditions were. More dust means more arid landscapes, and stronger winds to loft that dust into the atmosphere. The composition tells you where the dust came from, which in turn tells you about atmospheric circulation patterns. The size distribution tells you about wind strength and the distance the dust traveled. And what the dust reveals about the Eemian interglacial is both fascinating and troubling. For the first half of that warm period, roughly 128,000 to 125,000 years ago, dust levels were extremely low, even lower than during our current interglacial. This suggests warm, wet conditions with extensive vegetation, cover preventing soil erosion. But then, quite abruptly around 125,000 years ago, dust levels spiked dramatically. They increased by a factor of 10 to 20 in the span of just a few centuries. What happened? The evidence suggests a rapid drying of continental interiors, particularly in Asia and North Africa. Vegetation cover declined, exposing bare soil to wind erosion. The monsoons weakened or shifted, and crucially this happened while global temperatures were still relatively high. This wasn't a transition into a full ice age, but rather an abrupt shift within the interglacial period itself. The Eemian eventually gave way to the last ice age, but that transition took thousands of years. The dust spike around 125,000 years ago was something different. A rapid reorganization of the climate system that didn't fundamentally end the interglacial, but did make it significantly less hospitable, particularly in regions that depend on reliable monsoon rains. You're looking at this data because of what it might tell us about our own future. The Eemian is often studied as an analog for our current interglacial, the Holocene. Global temperatures during the Eemian were similar to or slightly warmer than today, though we're rapidly approaching and may soon exceed Eemian temperatures. Sea levels were 6 to 9 meters higher, as discussed earlier. But that dust spike suggests the Eemian climate wasn't stable. It underwent significant rapid changes even during its warm phase. Now here's where the 12,000-year cycle becomes relevant once again. When you examine the spacing of major climate transitions throughout the ice core record, certain timescales appear repeatedly. There are the 100,000-year cycles of ice ages and interglacials, driven primarily by variations in Earth's orbit, eccentricity. There are 41,000-year cycles related to the tilt of Earth's axis, obliquity. There are 23,000-year cycles related to the wobble of Earth's axis, precession. But superimposed on these orbital cycles are shorter, sharper transitions that don't fit neatly into the Milankovitch framework. These millennial-scale events, occurring every 1,000 to 15,000 years or so, show up consistently in multiple climate records. The Dansgaard-Oeschger events during the last ice age, for instance, were abrupt warming episodes occurring roughly every 1,500 years. The Heinrich events, marked by massive iceberg discharges, occurred roughly every 7,000 to 10,000 years. And when you look at the spacing of major dust spikes in the ice core record, you find a clustering around 10,000 to 15,000 year intervals. The dust, in other words, provides independent confirmation of what the temperature and ice records suggest. Earth's climate system has natural rhythms operating on millennial timescales, and these rhythms can produce abrupt, dramatic changes even within relatively stable climatic periods. Dr. Samuel Albani at the University of Milan has spent years creating global dust models that attempt to explain these patterns. When you meet with him, he shows you simulations that reveal something counterintuitive. Small changes in atmospheric circulation patterns can have enormous impacts on dust emissions and transport. A slight shift in the jet stream, a modest change in monsoon intensity, a small alteration in temperature gradients between ocean and land. Any of these can dramatically change where dust is generated and where it's deposited. This sensitivity means that dust doesn't just record climate change, it amplifies it. Dust particles in the atmosphere affect the radiation balance. They scatter and absorb sunlight. They can act as nuclei for cloud formation. They alter the reflectivity, albedo, of snow and ice when they settle on those surfaces. Dust deposited in the ocean provides iron and other nutrients to phytoplankton, potentially affecting ocean productivity and carbon uptake. In other words, changes in dust loading can feed back into the climate system, creating self-reinforcing cycles. Albani's models suggest that there are threshold behaviors in dust systems. Below a certain vegetation cover, dust emissions increase non-linearly. A 10% reduction in vegetation might lead to a 30% increase in dust. Above a certain wind speed, erosion increases dramatically. These thresholds mean that the transition from a low dust to a high dust state can happen rapidly, almost discontinuously, and we're seeing evidence of this happening now. You examine recent data from satellite observations and ground-based monitoring stations. Dust emissions from the Sahara and Sahel have increased significantly over the past few decades. Dust from Central Asia, particularly from the dried-up Aral seabed, has become a major environmental hazard. Parts of the Middle East are experiencing more frequent dust storms than in the historical record. Some of this is directly attributable to human activities, overgrazing, deforestation, poor irrigation practices that salinize and degrade soil. But some of it appears to be climate-related. Changing precipitation patterns, shifts in wind regimes, alterations in vegetation communities driven by temperature and CO2 changes. All of these are contributing to increased dust mobilization. The concern is that we might be approaching one of those threshold transitions. As the climate warms, several things happen that could dramatically increase dust. First, many continental interiors are projected to become drier under most climate models. The subtropics are expected to expand, pushing arid zones poleward. Mediterranean regions, the Middle East, the southwestern United States, southern Africa, southern Australia, all are projected to experience reduced precipitation and increased aridity. Second, vegetation patterns are shifting. Plant communities that have been stable for thousands of years are now experiencing unprecedented stress from heat, drought, and altered seasonal patterns. When these communities collapse, they often don't immediately transition to a new stable state. Instead, there's a period of bare soil, vulnerable to erosion. Third, the cryosphere, the frozen parts of Earth's system, is shrinking. Permafrost is thawing, exposing previously frozen soils. Glaciers are retreating, leaving behind unconsolidated sediments. These newly exposed surfaces are prime sources for dust generation. You visit the Taklamakan Desert in western China, one of the world's major dust source regions. The desert has been expanding, encroaching on formerly vegetated areas. Local residents tell you about dust storms that have become more frequent and more intense over the past few decades. Satellite data confirms this. The area of active dust emission has grown substantially. But what's particularly striking is the timing. You examine records of dust deposition in ice cores from the Tibetan Plateau, which receives dust from the Taklamakan and other Central Asian sources. The dust flux has been relatively stable for most of the Holocene, our current interglacial period covering the past 11,700 years. But in the most recent layers corresponding to the past few decades, there's a sharp uptick. Not yet as dramatic as the spikes seen in the Eemian ice cores, but heading in that direction. This matters because dust doesn't just affect local air quality. Dust from the Taklamakan travels thousands of kilometers, crossing the Pacific Ocean and depositing in North America. Dust from the Sahara crosses the Atlantic and affects air quality and ocean productivity in the Americas. Dust is a global phenomenon, and changes in dust loading can have planetary scale impacts. Dr. Natalie Mahowald at Cornell University has created models that attempt to quantify these impacts. Her work suggests that doubling global dust emissions could alter regional temperature and precipitation patterns, potentially triggering feedbacks that amplify the initial climate changes that increase the dust in the first place. In other words, we could enter a positive feedback loop. Warming causes, drying causes, dust causes further warming and drying. This is eerily similar to what appears to have happened during past climate transitions. The ice core records show that dust spikes often precede or coincide with major climate shifts. The mechanism isn't fully understood, but it likely involves multiple interconnected processes: dust affecting radiation balance, dust altering cloud formation, dust providing nutrients that change ocean biology and carbon cycling, dust darkening snow and ice, and reducing reflectivity, leading to faster melting. And here's the connection to the 12,000-year cycle. The dust record suggests that these feedback processes might have natural pacing. Looking at dust variations over the past 100,000 years, you see periods of relative quiescence punctuated by dust spikes roughly every 10,000 to 15,000 years. The timing isn't precise, this isn't a metronome, but the pattern is there, suggesting some underlying rhythm in how the Earth system transitions between states. We're now about 11,700 years into our current interglacial. If the pattern holds, we might be approaching another transition point, another period where dust could spike and amplify whatever other climate changes are occurring. And unlike during past transitions, we're now actively pushing the system with greenhouse gas emissions, land use changes, and other anthropogenic forcings. The combination is potentially dangerous. Natural variability might be priming the system for a transition, while our activities are providing the push that triggers it. The result could be a shift more rapid and more severe than would occur from either factor alone. You spend time examining the archaeological record from periods of past dust spikes. During the last ice age, high dust levels coincided with extremely harsh conditions for human populations. Many regions that are inhabited today would have been virtually uninhabitable. Chronic dust storms, poor air quality, reduced visibility, and damaged vegetation. But interestingly, some human populations adapted and even thrived in these conditions, developing strategies for coping with dust. Underground dwellings, protective clothing, methods for food storage that prevented dust contamination. But those were small, mobile populations with limited infrastructure. Modern civilization with its cities, its industrial agriculture, its complex supply chains, is far more vulnerable to sustained increases in dust. You think about what a significant global dust increase would mean: reduced solar panel efficiency, dust coating panels, increased respiratory illness, damaged crops, reduced visibility affecting transportation, accelerated degradation of infrastructure, impacts on water quality from dust-laden runoff, and altered weather patterns potentially reducing agricultural productivity. China has already experienced some of these impacts on a regional scale. During severe dust storms, cities like Beijing have had to shut down, with air quality reaching hazardous levels. The economic costs are substantial, billions of dollars annually in health impacts, agricultural losses, and infrastructure damage. Now imagine this occurring globally, not just as occasional events, but as a persistent condition. There's another aspect to the dust story that's particularly concerning: abruptness. The ice core records show that dust levels can change by a factor of 10 in just a few decades. This is faster than most other climate indicators respond. Temperature changes over centuries, ice sheets over millennia. But dust can spike rapidly because it's responding to surface conditions that can change quickly: a drought that kills vegetation, a wind pattern shift that increases erosion, a disturbance that exposes new dust sources. This means dust could be an early warning indicator, a canary in the coal mine for larger climate shifts. If we see dust levels rising sharply, it might signal that we're approaching a threshold, that the climate system is beginning a transition to a new state, and we are seeing that rise. Global dust emissions are estimated to have increased by 25 to 50% since pre-industrial times, with most of that increase occurring in recent decades. Parts of the Middle East have seen dust storm frequency triple since the 1990s. The Arctic, as permafrost thaws and glaciers retreat, is becoming a significant dust source for the first time in thousands of years. You attend a conference in Lanzhou, China, a city that experiences some of the world's most severe dust storms. Researchers from around the world present data showing increased dust across nearly all major source regions. But what's striking is that they're also finding dust in places it shouldn't be. Dust types that suggest changes in atmospheric circulation are carrying particles to new locations, creating novel deposition patterns that could affect ecosystems unprepared for this input. Dr. Jasper Koch from UCLA presents work on what he calls dusty futures, scenarios for how dust loading might evolve under different climate change pathways. Even under relatively optimistic emission scenarios, his models predict significant increases in dust from some regions with complex patterns of winners and losers. Some agricultural regions might benefit from increased nutrient deposition, while others suffer from reduced sunlight and increased erosion. But in the high emission scenarios, the predictions are stark. Parts of the subtropics could see dust emissions increase by 200 to 300%, creating conditions comparable to the dustiest periods of the ice ages. This wouldn't just be uncomfortable, it could make some regions functionally uninhabitable for modern agricultural and urban systems. The question you keep returning to is, are we witnessing the beginning of a dust spike comparable to what occurred in the Eemian? Are we triggering one of those millennial-scale transitions that show up in the paleoclimate record? The data is still ambiguous. We're only a few decades into the current trend, which is far too short to confidently identify a long-term shift. But the trajectory is concerning, and it's occurring at a time when other indicators, ice melt, ocean circulation changes, magnetic field weakening, also suggest potential instability. The dust speaks if we listen. It tells of past transitions, of rapid shifts from stable to unstable states, of feedback loops that can amplify small changes into dramatic transformations. And it whispers a warning about our current trajectory, about the possibility that we're recreating conditions that in the past heralded major climate reorganizations. As you fly over the Taklamakan Desert, you can see the dust plumes extending for hundreds of kilometers downwind. From 30,000 feet, the desert looks vast, implacable, eternal. But you know from the records locked in ice and sediment that this landscape has changed dramatically many times. It has been wetter, greener, more hospitable. It has been drier, dustier, more hostile. And it will change again. The question is whether that change will be gradual, manageable, something we can adapt to, or whether it will be abrupt, a threshold crossed into a new, dustier, harsher state from which there may be no easy return. The dust continues to rise, to travel, to settle, writing in its deposition patterns a story whose ending has not yet been determined. But the opening chapters, visible in the ice and soil of ages past, suggest we should pay close attention to what comes next.